Okay, we are recording. So today I'm going to do a small portion of lecture, and then we are going to do exercises to get familiar with all this new vocabulary that we have seen in the last two classes. No? So let's say that you have a PC that is in Paris that want to communicate with a laptop that is in Japan. So for example, this PC is connected to an Ethernet network. So here we use UTP cable, and it is based on copper. Then let's say that this router is connected through fiber optic to a dish antenna. So this is fiber optic here that we are using. This can be multi-mode fiber optic or monomode fiber optic. And you know that inside this medium, we use pulse of light. Then this dish antenna is in communication with a satellite. So here we have a wireless communication. And of course, there is another dish antenna in Japan. So the satellite connect the one that is in France with the one that is in Japan. And this dish antenna through fiber optic is connected for example, to a Wi-Fi router. And through Wi-Fi, which is a wireless communication, you connect this laptop. So what is changing here is layer 2, which is the data link layer, and layer 1, which is the physical layer, what we are changing here. So here we have Ethernet, here we have fiber optic, here we have satellite links, fiber optic and Wi-Fi. This is very common. Remember that the data link layer is divided in two sublayers. The max sublayer, which is the lower sublayer, and the LLC sublayer, which is the upper sublayer. One of the objective of the LLC sublayer is to make all the layers that are above to be independent of the hardware. So layer 3 is totally independent of the hardware. Layer 3 up are layers that are independent of the hardware. Okay, so there is a term that is called get access to the medium. To get access to the medium, we need to define some rules, how we are going to access the medium, because the medium is shared. So we do need some rules, and we will see that a frame that go, for example, from this computer to this router, will have a first hop. When it arrives in this router, it will go up the stack. While it goes up the stack, it will be susceptible to what we call decapsulation. And when it will go down the stack, it will be susceptible of what we call encapsulation. Then there will be a second hop. And when it arrives to this router, the same thing. The router, when it will go up the stack, will do decapsulation. And when it goes down the stack again, will do encapsulation. No? So this slide explains a little better the things. So a PC has 7 layers. And a server also has 7 layers. In general, end devices have the 7 layers. Now, the router is a layer 3 device. And a switch is a layer 2 device, as we will see. So let's say that this computer has something to send to the server. So the information that this computer generates at the level of the user will go down the stack. And while it goes down the stack, it will be subject to encapsulation, which means that every time that I pass through a layer, the layer is going to add information to the data. It's going to add a header to the data. So for example, here in the transport layer, we have TCP or we have UDP. They will add a TCP header if we are talking about TCP, or a UDP header if you are talking about UDP. In the network layer where we have IP is going to add its own header. In the data link layer, this is Ethernet. So Ethernet is going to add its own header. And then in the physical layer, the PDU, which is a series of bits, will be converted through a process that is called encoding to a signal that can travel into the medium, into the Ethernet cable. Okay, so this signal will travel, and R1 will do the inverse operation. It will receive the signal and decode the signal. Decode is transforming a signal to a series of 0 and 1. And the information will go up the stack. The router go up to layer 3. So in layer 1, I will decode, which means I will transform the signal into a series of bits. In the data link layer, there is an Ethernet header. In the Ethernet header, we have a destination MAC address. So I will check that it is my MAC address on this interface. There is a source address. It should be the MAC address of this PC. And the data link layer will tell me what is the payload, what is in the payload of the frame. And it will say, please send that to IP. So I will go up in the layer, and IP will check the IP header. And using the routing table, it will take a decision what to do with the packet. So the packet will go down the stack. When it goes down the stack, I will add header, which means I will encapsulate. For example, the data link layer is going to put a header that corresponds to a serial link. And the physical layer is going to encode the series of bits into a signal that can traverse a serial link. When this is received by R2, it will also go up the stack, up to layer 3, because R2 is a layer 3 device, and down the stack. It will traverse the medium and will finally arrive to the server. And when it arrives to the server is going to decode the signal, change it into a series of 0 and 1. That will be done in the physical layer. In the data link layer, I will check the Ethernet header because this link is an Ethernet link. So I will check that the destination MAC address is the MAC address of the server. And in the data link header, there is information to whom we should give the data in the upper layer. So for example, it might be to IP. If it is the case in the upper layer, in layer 3, where is the network layer, I will give the data after removing my header, which is the Ethernet header, I will give it to IP. IP will check also the header, remove it, and give it to the transport layer. The transport layer will check it's either remove it, and it will go up the stack like that. So each layer will be consulted in the corresponding layer. Each header will be consulted in the corresponding layer and will be removed. And this is called decapsulation. So when I receive, I decapsulate. Look here, we have a PC, a switch, a router, a switch, and a server. So the PC is a layer 7 device. The switch is a layer 2 device. The router is a layer 3 device. The switch is a layer 2 device. And this is an end device. The end device are layer 7 devices. So let's say that this PC wants to send something to the server. It will go down the stack in the PC, and it will be subject to encapsulation, which means that each layer will add information to the data when it goes down the stack. So it will eventually be encoded and will traverse the medium and will be received by switch 1. When switch 1 receives it, it will go up the stack, up to layer 2, and then will go down the stack and will traverse the medium again. When it's arrived to the router, it will go up the stack, up to layer 3 and down the stack. And it will traverse the medium. Then when it's arrived here in switch 2, it will go up the stack, then down the stack, and traverse the medium, and finally it will arrive to the server and go up the medium. So let's say that we use TCP. So if it is the case in the transport layer here, TCP added a TCP header. This header is for the TCP that is running in the server. This is what we call this peer-to-peer communication, which is the TCP running in this machine wants to be in communication with the TCP running in this machine. And they understand each other because both of them are TCP. Both of them are implementation of the TCP protocol. Look, when the data go down the stack, IP had a header. This header will be consulted by R1 because it will go up the stack until up to IP. So IP will consult it, make modification on the header, and send it back to the network. And when it will go up the stack here in the network layer, this header that was initially put by this PC will be removed by the server. Of course, it will look at the data that is inside and remove it. Removing the header is called decapsulation. Okay, here are some organizations that do standard for the data link layer. Okay, so I want to talk about a little more about accessing the medium. So when something is shared between several entities, we need rules so that one of the entity can use it. So the transport, the media in a network is something that we share, and only one device at a time can access the medium. So to make an analogy with something that exists, let's say that we have a road, like for example, a highway, and you are in your car and you want to enter the highway. So in general, we have rules to know when we can enter a highway or when we can enter a road. So for example, the most frequently way for you to enter a highway is that we have acceleration lane that enter the highway. So you come, you are in the acceleration lane, you start to accelerate your car, and be sure that you can insert between the vehicles that are already on the highway. So we do have rules. And the vehicles that are already on the highway are the ones that have priority. And since we are going to share the highway, we do need rules so we don't have an accident. When you are going to enter a road, not a highway, there are different ways to enter the road. So one way is, for example, you have a stop sign. And when you arrive to the stop sign, you stop your car, check the traffic on both sides, and if you can enter, you enter. When you can enter, you enter. So you do follow some rules because the road is shared between different cars. Or another way to enter a road is the road is controlled by a traffic light. So if you arrive and the traffic light is in red, you stop your car until the traffic light changes to green. And when the traffic light is green, you can go to this road that you are pretending to enter, no? So if we didn't have rules to drive, it will be like that anyone will driving without considering the other one. And this will create serious problem, no? A lot of accident, and of course, this is exactly the same thing for the network, because the network is a shared medium, is shared between several devices. So we do need rules to take the medium to start transmitting. Okay, we cannot just start transmitting without considering that there are other stations that might want to do the same thing that I want to do, which is transmitting, no? Okay, what is the physical topology? The physical topology is what you see physically. It doesn't mean that because physically you see a certain topology, that logically it will work as what you see physically. The logical topology can be different from the physical topology. For example, Ethernet is logically a bus, but physically today Ethernet, we use switch, it's physically look like a star, but it is not logically a star. Logically it is a bus, as we will see. So one thing is the physical topology, which is in layer 1, and another thing is the logical topology, which is in layer 2. So the physical topology, as I was telling you, is how you see it physically. The infrastructure, how you connect the end devices to switches and switches to router. This is the physical topology. Now, the logical topology refers to the way that the network transfers frame from one node to the next node. Okay, so it's more higher level, and it doesn't have to correspond to the physical topology. It's more the way that we transmit, the frame inside the topology that is important for the logical topology. So let's talk about the different topology that we use in computer networking. This topology, where we have only two nodes that are connected through a link, is called a point-to-point communication. So if this device sends something, it's for the other device, because you can only connect two devices in a point-to-point connection. And what this device is going to send is for the other devices. Okay, this topology is called the hub and spoke topology. So in the center, we have a central device that is called the hub. And all the other devices are called spoke, and they are connected to the hub. So this is a central point of connection, the hub. And the spoke just connect to the hub. So this topology in general is cheap, because let's say that I have a company. This is the main part of the company, and those are branches. So the branches just connect to the main part of the company, to the main building of the company. If this branch wants to communicate with this branch, the traffic has to go through the main company. So this is cheap because I just have one link between each branch and the main part of the company. So it's very cheap. Now it's not tolerant to fault. Let's say that they break this link, this branch will not have access to the information of the company anymore, because you cut this connection. So it's not tolerant to fault. It's very sensitive to fault. This topology is a mesh. It can be a full mesh. If it's a full mesh, we have all against all. So in this case, it's a full mesh. If you look at this node, it's connected to all the other nodes. So it's connected here through this link. It is connected through this link to this other node. It is connected through this link to this other node. It is connected through this lead to this node. And it is connected through this link to this node. So this topology have a lot of redundancy, which is good, because you can break several links and the communication still work. The problem with a full mesh is that it is very expensive. You need a lot of link between the devices, and of course, all the devices need to have a lot of network interface card. Because, for example, in this one that I have 1, 2, 3, 4, 5, 6 nodes, you see that each node is connected to the other 5 nodes, which means that I need 5 wireless, I need 5 network cards. In general, if there are n nodes, I will need n-1 network card, which is very expensive. And the number of connections grow exponentially, the number of links that I need. So in general, because of the cost, full mesh are not frequent. And what we have is partial mesh. So we do put some redundancy because we like the redundancy, but we control how much redundancy we will have. So here we have a slide to come back and talk about a physical point-to-point connection. So in the physical point-to-point connection, we connect two devices through a physical link, and there is nothing in between them. So what R1 sent on this link is for R2. What R2 sent on this link is for R1, because we can only have two devices. And in serial connection like that, there are several protocols that we can use in layer 2. So for example, we can use point-to-point protocol, we can use serial line internet protocol, or we can use high-level data link control protocol. By default, when you have a serial link in Cisco, the encapsulation that it uses is this one, which is high-level data link control protocol. But you can change it if you want to PPP, point-to-point protocol. Now, this is a physical connection. Now, you can still have a point-to-point connection between two devices, but between them, you have maybe something that is very complex. So you just put a cloud. So physically, it's not a point-to-point connection, but logically, it will be a point-to-point connection, which means that R1 and R2 are not aware that they are separated with many devices. They just think they communicate to each other directly. So it's just the impression. But physically, we have here a lot of devices. So this is what I was telling you. One thing is the physical topology. Here, the physical topology is a point-to-point topology. And another thing is the logical topology, which is in layer 2. So logically, R1 and R2 have the impression that they are directly connected through a point-to-point network, but in fact, they are not. Okay? In the cloud, we can have something that is very complex. For example, we can have layer 3 devices or layer 2 devices in the cloud, no? But for those two guys, it's like there is only one point-to-point link, when in reality, it is not a point-to-point link. Let's keep talking about topology. So this is called a star topology. In a star topology, you do have a device here in the middle, but this device acts more like a concentrator and does not change the information of the frame that it receives. This is called an extended star. So an extended star is a star of stars. So as you can see here, we have a star, we have another star, and when you interconnect stars between each other, you call that an extended star. So the connection that we have in modern Ethernet is this physical topology, which is extended star. Another possibility is a ring. For example, token ring and FDDI use a ring, where the computers are connecting inside the ring together. Another possibility is a bus topology. That was the first topology that we have for Ethernet. We used to have a bus topology. Those connectors are called T connector, and here we have N connector that we use to avoid that the signal bounce back into the bus. So let's say that this station transmit, it's go through this cable, some of the signal go on this way, and other of the signal go on this way. The one that's go on this way will be absorbed by a terminator here. The objective of the terminator is to absorb the signal and avoid that the signal bounce back into the medium. Okay, I already explained what was simplex, half duplex, and full duplex, but here we have some slides. So remember, we say that a communication between A and B is simplex, is, for example, the only communication that exists is A sending to B, but B cannot send to A. So that will be a simplex communication. Example of simplex communication is a radio that broadcasts a signal, or for example, a TV channel that broadcasts its signal. In this case, it's a simplex communication because the signal of the radio is broadcasted, so it just goes from the radio to the end devices. But you cannot interfere, you cannot send information through this communication channel. So half duplex. These two devices, for example, have half duplex if the server can send to the hub and the hub can send to the server. If we can do that, we said it is half duplex, and in half duplex they cannot communicate at the same time, which means that if device A is sending to device B must wait the end of the communication from device A to send some data on the network. Okay, so it's not full duplex, it is just half duplex, but it's allow communication on both sides. You just have to take turn. At one point it's my turn, then at another point it's your turn to transmit. And full duplex is when we can send and receive at the same time. So A can send to B, B can send to A. And we can do that at the same time. For example, modern Ethernet devices are full duplex. So at the level of the UTP cable, half duplex was what we implemented many years ago. Although Ethernet was half duplex. And in a cable where we have 4 pairs, we will use the same pair of cable to send and receive. So we can have collision. For example, I can decide to send something when another station also decide to send something. If we send both at the same time, we will have a collision. So full duplex today use of the 4 pair of cable that we have in a UTP cable, full duplex will use 2 pair. 1 pair to transmit and a different pair to receive. It's not like half duplex Ethernet a few years ago that will use the same pair of cable to transmit and receive. So in half duplex, you do have collision because the 2 devices that are connected together might take the decision to transmit at the same time. If they do so, then we will have a collision, and the station will use the binary exponential back-off algorithm to come back from the collision. Okay, When I share a medium, as I was telling you, we need a way to access the medium. This is called the method to access the medium. So some of those medium are specified here. We will come back to them. Carrier sense multiple access with collision detection is used by Ethernet. Carrier sense multiple access with collision avoidance is used by Wi-Fi. And we'll see why Ethernet use collision avoidance and why Wi-Fi use Ethernet use collision detection and why Wi-Fi use collision avoidance. No, we will see that. So let me explain you how in a ring topology how we will access the medium. So a few years ago, IBM created a network that is called token ring. And the way that we will access the medium in token ring is through a token. So I'm going to do a graphic to explain you how token ring work. So let me open Paint and let me explain it. So you have a ring, the topology, the logical topology is a ring. Physically, it's look most of the time, it will look like a star, but the logical topology is a ring. So you have one station here. Let me call it STA1. You have another station here. Let me call it STA2. You have another station here. Another station here. Another station here. Okay, so STA3, STA4, on station 5. So in token ring, we have a ring, and we have a way to send the data. So we send the data, for example, in this direction. So to control the medium, there is a token that circulates the ring. So let's say that in this moment, the token is in station 1. And station 1 have nothing to send. So station 1 is going to send the token to the next station in the ring, which is station 2. So station 2 receives the token, and if station 2 has something to transmit, it will transmit. Let's say that station 2 have nothing to transmit, so it sends it to the next station in the ring, which is station 3. Let's say that station 3 have nothing to send, it sends it to the next station, which is station 4. Let's say that now that station 2 has something to send. It has to wait. So station 4 had the token. It have nothing to send, it sends it to station 5. Let's say that station 5 has nothing to send. It received the token, since it have nothing to send, it sends the token to station 1. Remember that station 2 is waiting to send data. So station 1 received the token, it have nothing to send, it sends the token to station 2. Finally, station 2 that was waiting to transmit got the token. So station 2 is going to remove the token from the ring and send its data. Let's say that the data is for station 5. So I want to do a transmission between station 2 and station 5. So station 2 remove the token from the ring and send the data that is for station 5. So this data will go over the ring. So station 3 will receive the data, and we'll see that the destination MAC address is not its MAC address. So station 3 is just going to forward the data on the ring. So it will arrive to station 4. Station 4 will do the same. It will look at the destination MAC address. It's not my MAC address. So station 4 is going to forward the frame over the ring to station 5. So finally, it's arrived to the destination. So station 5 will see that the destination MAC address is its MAC address. So station 5 will make a copy of the frame. And after that, we forward it to station 1. Station 1 will see the MAC address of the frame. It's not its MAC address. So station 1 will just forward the frame to station 2. So the sender was station 2, and the frame came back to station 2. So station 2 realized that it's the frame that it's sent. It will remove the frame from the ring and now release the token. So the token will go to station 3. If station 3 have nothing to send, station 3 will send the token to station 4. If station 4 have nothing to send, station 4 will send the token to station 5. And the token will go around until a station has something to send. And when this station has something to send, it will remove the token and put a frame inside the ring. The frame will give the whole round and come back to the source, the station that wanted to send something. This station will remove the frame and it will release the token again. So for you to transmit, you do need to wait the token. So can you please tell me what will be the benefit of this way of controlling the access to the medium? What do you think that will be the benefit? Can we have collision? No, we cannot have collision because I cannot transmit. To transmit, I need to wait the token. Once I receive the token, I can transmit. I can remove the token from the ring and send the data that I want to send. The data will go all over the ring and come back to me. When it's come back to me, I remove the data from the ring and I release again the token so another station can transmit. So there is no collision in token ring. And by the way, the name that we give to this method of accessing the medium is called token passing. Token passing. I need the token to transmit. So benefit of token passing is that we don't have collision. Now, if I ask you, do you think that token passing scale well? Which means that if we add more stations, do you think that the communication is still going to perform well? Yes, it will perform well because we don't have contention in token passing. We just have to wait the token if we want to transmit. All the medium do have contention. So all the stations that want to access the medium compete for the transmission medium. In token passing, we don't have to compete. We just have to wait the token. And when the token arrives, we remove the token from the ring and insert, as a replacement, we insert the frame that we want to transmit. No? So token rings scale very well. Token ring also, we know that after some time, I will be able to transmit. This is not the case of Ethernet. Ethernet is based on contention. We compete for the medium. Here we don't compete for the medium. We just have to wait the time, some time to be able to transmit. And eventually a token will arrive to us and we will be able to remove this token from the ring and to send our data. So that is the way that token ring works. No? The method is called token passing. So now I'm going to explain you the contention medium of Ethernet and the method to access the medium. It is called carrier sense multiple access with collision detection, as you can see here, no? So we do use collision detection here. Sorry, I did what I didn't want to do. I'm trying to maximize. So here, carrier sense multiple access with collision detection, Ethernet is able to detect collision. So let me explain you how Ethernet works. So we have a shared medium. Let's say that we have several stations. Let's say that station 1 wants to transmit. So the first thing that is going to do station 1 is to listen the medium. It will going to listen the medium to see if another station is already transmitting. So if another station is already transmitting, station 1 will detect the carrier on the link and will know that another station is transmitting. So in this case, if another station is transmitting, I have to wait until the end of the transmission. I cannot transmit while another station is transmitting, because if I transmit at the same time, I will have a collision. A collision is the superposition of the two signals. And at the end, the result is just noise. So when we have a collision, we have to find a way to come back and to try to send the frame again. So Ethernet do try to detect collision. So let's say that I listen the medium, it is busy, I have to wait. Now let's say that station 1 have to send something and the medium is free. So the communication that was going on, just stop it. And the medium is free. Station 1 know that the medium is free because there is no carrier detected on the medium. So station 1 can transmit because the medium is free. If no other station transmits at the same time, that will be fine. So the signal of station 1 will propagate all over the network, and the destination station will receive this frame. So when a station transmits, it also listens the medium. If what I'm transmitting is what I am listening, it means that there were no collision. And if there were no collision, I can assume that what I was transmitted was received by the destination. So Ethernet, for example, don't retransmit if I don't detect a collision, which means I'm transmitting and I'm listening what I'm transmitting, I see the same thing. So there is no collision. I assume that the destination received my frame. And in Ethernet, there is no ASECA. There is no acknowledgement. Now, let's say that station 1 and station 2 both want to transmit. So both of them listen to the medium. Let's say that no other station is transmitting. So they might, unfortunately, at the same time, start transmitting. And it's when we have a collision. If they start transmitting at the same time, the collision will be detected by both stations. Why? because while they transmit, they also listen. If I detect a collision, I need to recover from the collision. And the algorithm that Ethernet uses is called BEB, binary exponential backoff. So let's say that the two stations listen to the medium is idle, there is no carrier, they transmit at the same time, and they listen what they are transmitting. So eventually the two signals will arrive in collision, and the station are going to listen a signal that is noise, that is not what they are transmitting. If they detect that, they know that a collision occurred. So in this case, all the stations that are involved in the collision have to get a random number between 0 and 1. So it can be either 0 or 1. Let's say that both stations choose the random number 0. If both choose the random number 0, they can retransmit right away. They don't have to wait. They have to wait 0 period of time before retransmitting. So they both are going to listen to the medium and are going to try to retransmit. Since the medium will be idle, they are going to retransmit at the same time, and we will have another collision. So if both have 0, we will have another collision. Let's say now that one station got the random number 0 and the other station got the random number 1. So the one that got the random number 0 means that it can retransmit right away. And the one that got the random number 1 have to wait 1 period of time before retransmitting. So which means that the station that got 0 is going to retransmit first. And of course, listening what he is transmitting. So when the period of time that the other station that got 1 ends, this station will start listening the medium to see if the medium is busy. It will see that the medium is busy because the first station already started to send, so it will have to wait. And it will be able to transmit what you have to transmit only after the communication of the first station. So the best case is when one station have 0 and the other station have 1. Or the first station have 1 and the second station have 0. This is the base case because they will not try to retransmit at the same time. Okay, let's see this example. I just got into a collision with another station. So we are going to use the binary exponential backoff. I take a random number, I got 1. And the other station also got 1. What will happen if both got 1? What does this 1 mean? That both of the stations that were involved in the collision have to wait 1 period of time before retransmitting. So both of them are going to wait 1 period of time. After 1 period of time, both of them are going to listen to the medium, and both of them are going to see that the medium is idle. So both of them are going to retransmit at the same time what they were trying to transmit. And we will have a second collision. So if both of them have the same number, we have a second collision. If both of them have different number, we will be able to retransmit in a synchronous way. So let's say that the two stations that got the initial collision retransmit at the same time because both of them got 0 or both of them got 1. What will happen? This time, when they are going to also take another random number. But this time the interval will be 2 times bigger. So they are going to change a random number between 0 and 3. It can be 0, it can be 1, it can be 2, or it can be 3. So if both stations take the random number 0, or both take the random number 1, or both take the random number 2, or both take the random number 3, what will happen? Let's say that both take the random number 2. What will happen? They both have to wait 2 time intervals before trying to retransmit. So they both will wait 2 times the interval, no? The interval that they have to wait. After that, both stations will listen the medium. Then we see that the medium is idle, and they are both going to retransmit at the same time. So we'll have a third collision if both stations have the same number. Now, if one station have 1 and the other station have, for example, 2, what will happen? When they got the random number, one station got 1 and the other station got, for example, 2 or 3. Let's say 1 and 3. What will happen? The station that got 1 have to wait 1 period of time. So it will wait 1 period of time. After 1 period of time, it will realize that the medium is idle and will start transmitting. Now, the station that got 3 have to wait 3 periods of time. When finally this 3 period of time end, what will happen? The station will realize that the other station is already transmitting, so it will have to wait. And when the other station ends transmitting, this station will be able to transmit. So the problem is when we get 2 times the same random number. So 2 times 0, or 2 times 1, or 2 times 2, or 2 times 3. If we got different random number, we will not have a collision. So let's say that after the second intent, they got a collision again, because both of them, let's say that got 1. What will happen? So now instead of choosing random number between 0 and 3, we are going to choose random number between 0 and 7. So we multiply the interval by 2, the size of the interval. So we are going to choose random number between 0 and 7. If we choose 2 different random number, there is no problem. If we choose the same random number, what will happen? We will have another collision. And we will have to choose again random number. So why do you think that the interval that we consider for the random number, we multiply it by 2 every time? Why do you think that we do that? Well, if, let's say, those 2 stations take random number between 0 and 1, the probability that they take the same number is very high, because it can be either 0 or 1. So the probability that both take 0 or both take 1 is very high. Now, if we choose a random number between 0 and 3, the probability of taking random number and that the random number is the same is less. If we take random number between 0 and 7, because the interval is bigger, the probability that we take the same random number is even less. So if we still have a collision, we multiply the interval by 2. So we go between 0 and 15. If we still have a collision, we go between 0 and 31. If we still have a collision, we go between 0 and 63. If we still have a collision, we go between 0 and 127. At one point, we should be able to choose random number that are not the same. If the random number are not the same, the transmission will be successful. So this algorithm is called binary exponential backoff. The binary comes from the fact that we increase the size of the interval by 2. We multiply the interval by 2 to reduce the probability of having another collision by 2. Okay? So this is the way that carrier sense multiple access with collision detection work. Now, let me go to carrier sense multiple access with collision avoidance. Wi-Fi use this. So the problem in wireless network, it is difficult to detect a collision. So since it is difficult to detect a collision, what we are going to do is we are going to try to avoid collision. So in Internet, we don't have an acknowledgement. We send a frame, and if we don't listen a collision while we are sending the frame, we assume that the frame was received by the destination. In Wi-Fi, since we are not able to detect a collision, we are going to use an acknowledge, which means that when a station A wants to send a frame to a station B, so it will send a frame, which is a frame of data, but station B will have to send, after receiving the frame, it will have to send an acknowledgement to station A, telling station A, hey, I got this frame from you, and I'm confirming that I received the frame. Why we need an acknowledgement? Because it's very difficult to detect a collision. So let's see how carrier sense multiple access with collision avoidance work. Let's say that this station wants to transmit something. So first, it will listen the medium, which is the air. If I cannot detect a signal in the air, which means that nobody is transmitting, I can start transmitting. Eventually, the destination station is going to receive the frame, and this station will have to send an acknowledgement back to me. When I receive the acknowledgement, I know that the frame that I just transmit was received. If I don't receive an acknowledgement, I will try to resend the frame, waiting for the acknowledgement to arrive. So the way that the station in Ethernet know that the destination have received the frame is through the acknowledgement. So every time that we send a frame, there is an acknowledgement that say, okay, we did receive the frame. Now, Ethernet is very simple, the Ethernet header. The Wi-Fi header is much more complex. There is a field that is called NAV, N-A-V. So in AAV, I put a number of microsecond or millisecond that I'm reserving the media. So when I start transmitting, for example, let's say that I need to transmit a frame and I need to receive the acknowledgement that is associated with the frame. I will compute an estimation of time that I need to send the frame and to receive the acknowledgement. When I send the frame, I put this information in the frame. Let's say that I put 20 milliseconds in this field, which is called a nav. It's just informed the other station that for 20 milliseconds, they should not use the transmission media, because I'm going to use it either to finish my transmission or to receive the acknowledgement from the destination station. So Wi-Fi is much more complex because it has this nav field, which is a way to reserve the medium. So as we say, a frame have always a header, it have payload, and it have a trailer. In the trailer, what we generally have is a CRC, a cyclic redundancy check, or another word to say that is a frame check sequence, FCS, a frame check sequence, no? Okay, let's talk about MAC addresses. So, according to the manufacturer, some manufacturer will show you the MAC addresses like that. So you have a byte, dash another byte, dash another byte, 6 times. So the MAC address is 48 bits because 6 times 8 is 48 bits. So some manufacturers use the dash to separate each byte of the MAC address. Other manufacturers, for example, use the colon to separate each byte of the MAC address. And others, like Cisco, use the dot. And instead of separating 1 byte at a time, they separate, the dot separate a group of 2 bytes. So this is the way that Cisco represents the MAC address, and those are other manufacturers. So when you do an exercise, like a homework, or you go for a quiz or an exam, and they ask you a MAC address, you can write the MAC address in any of these 3 forms, and it will be valid. Okay, because this is the 3 ways that people write MAC addresses. So a MAC address, as I was telling you, is 6 byte long or 48 bit long. And the MAC addresses are controlled by the IEEE, the Institute of Electrical and Electronic Engineer. So those are examples of MAC addresses. This one, this one. So here we use the dash notation. Here we use the colon notation, and here we use the dot notation. Remember that when we use the dot notation, here we have 2 bytes, dot 2 byte, dot 2 byte, for a total of 6 bytes, no? So IEEE is the one that controls the MAC address, the distribution of MAC addresses. So they give blocks of MAC address to manufacturers so they can construct network devices. When the manufacturer run out of block, it has to contact IEEE again, and there is a cost to have a MAC address, no? To have what we call an organizational unique identifier. So the organizational unique identifier is an identifier that IEEE will give to the manufacturer. And in fact, is the first 3 bytes. So for example, if I take this MAC address, the organizational unique identifier is this first 3 bytes, 00, D0, BC. If I take this address, the second one, this is the organizational unique identifier. B4, 6F, 6B, sorry, FC. So let's see the organizational unique identifier that were already assigned by the IEEE. So I'm going to copy this URL, and we are going to visualize this URL. So look at, I just put the link in my browser and look at what we have. If the organizational unique identifier starts with 002272, it belongs to American Microfuel Devices Corporation. Okay, so here the IEEE maintain information of which organizational unique identifier was sold, and to which company. For example, look at here, we have Cisco system. So this F4BD9E is one of the organizational unique identifier that got Cisco. But Cisco is a so big company and they produce so many network devices that they run out of MAC addresses for this organizational unique identifier. So what they did is to buy another organizational unique identifier. So let me show you, for example, with the company Cisco. So here we have a first organizational unique identifier for Cisco, which is 084B A9. But Cisco has several. Let me keep searching. Look at, you have another one here, 084F F9. Let me continue, and we have another one here, 0088A2 belong to Cisco system. And there are several that belong to Cisco system, no? Because they need them, because they are selling router and switch. So they need to put MAC addresses inside those devices that they will be selling, no? Let me see if I forward something here. I think no. Okay, so this is the structure of a MAC address. So the first 24 bits are called the organizational unique identifier. You need to buy, if you are a company, you need to buy a OUI to either your local rear or to you need to get an organizational unique identifier through IEEE, sorry, no? Because those organizational unique identifier, you get them from IEEE. So these 3 bytes identify a manufacturer. And these 3 bytes, which is 24 bits, are free for the manufacturer to create network interface card. So what they do, every time that they create a new network interface card, they burn in the network interface card a MAC address, one of this one, no? For each organizational unique identifier, I can create 2 to the power of 24 different network interface, because for each network interface, I need a MAC address, no? Okay. I just finished lecturing for today. So let's see, do you have any question first? No? Okay, let's, so. Let me search for the exercises that we are going to do today. I think it's exercise 4. Yes. So let's see. Question 1. Which statement describes the characteristic of a convergent network? So in the past, we have company will have 3 different networks. A network for the telephone, a network for the data, and a network for the video camera, for the security system. So they will have to implement 3 different wiring inside the company. The wiring for the telephone network, the wiring for the data network, and the wiring for the security network with camera in different places of the company, and they will monitor what this camera is recording, no? So what was the bad thing with having 3 different networks is that it was very expensive. You need to run connection for the 3 different networks. Today, with the versatility of IP, we just use 1 network. And over this network, we put telephone, data, and video. So we just have to run cable for 1 network. And all the information go over this network. So it's much cheaper in installation and much cheaper also to maintain the network, because we don't have to put 3 different networks. So this is called a triple play also. In 1 network, we put 3 players: the telephone network, the data network, and the security network. So let's see the question. Which statement describes a characteristic of a convergent network? So it says a single network that delivers voice, video, and data to a variety of devices. This is question A, answer A. Answer B say a network establishes separate communication channel for each network service. So that was in the past. In the past, we have a network for telephone, a different network for data, and a different network for security. Today is the same network. So answer B is not the answer, no? Let's see C. The network uses different technology for voice, video, and data. That was the past. Today, we use the same network to pass the 3 needs that we have, which is data, which is video for security, and telephone, no? Let's see answer D. The network services are delivered over a wide range of network platforms. So the answer here was A, no? You have a single network that will deliver voice, data, and video to everybody. So the answer was A. Let's see question 2. Refer to the exhibit. Which term correctly describes the devices that are included in area B? So this is area A, this is area B, and this is area C. So they want you to tell those devices which term correctly identify them. So look at the possibility. They are source device, they are end device, they are transfer device, they are intermediary device, they are destination devices. What do you think? What will be the correct answer here? The one that are in the area B. So if I ask you, for example, this PC is what? In all this, it is what? It will be the source of traffic, and it will also be the destination of traffic. So if, for example, I send something to the printer, I am the source of the traffic. I have a file, I want to print the file. So I'm the source of the traffic. Now, if, for example, I navigate the web, I go to a website, I will be the destination of the web server. The web server will generates packet that it will send me, so I can reproduce them or render them in my web browser. So those devices that are here are what? They are source and end devices. Source because they will emit package, and because they will receive package from a web server, for example. So they are source and end devices. What about the ones that are here in the middle? They are what? So they are intermediate devices, which means that they receive a frame on one interface, look what they have to do with the frame, and send the frame back using another interface. So they are intermediate devices. Okay? Let's see question 3. Match the internet connectivity type, which is here on the left, to the appropriate description or characteristic, which is here on the right. Not all options are used. So if you see here, we have 5 options, and here we have 6 description of the characteristics. So of course, it will not be a one-to-one. There will one here that will be left out. So what can we say about Metro Ethernet? So Metro Ethernet is the usage of Ethernet in a city. Metro come from metropolitan area Ethernet. So normally, where do we use Ethernet? In LAN, in local area network. Like here, we have Ethernet. But normally, the distance in Ethernet is small. So recently, they came with this technology that is called Metro Ethernet, where the distance can be up to some miles away. So it's very good for cities. So what can I say? Metro Ethernet, what will be Metro Ethernet? It will be 1, 2, 3, 4, 5, or 6. So Metro Ethernet will be what? Let's see what they say here. Signal carried on the same copper or fiber medium as the television signal. What is that? You have cable TV at home or cable internet. You might have that because we don't have a lot of choice in Jacksonville. We go either with AT&T, which use ADSL, which means telephone line, or we go with Sparklight, and Sparklight you have a coaxial cable that arrives to your house if you want cable TV, and they can bundle on top of the cable TV. They can bundle the internet also. So this is called cable. So one, go with cable. Now let's see 2. Access via the cell phone network. So these 2 will be what? The cellular network. The telephone network that we use today with your cellular phone, use the cellular network. So this one, the 2 will correspond to cellular. So 2 go with E. So let's see 3. Require a dish and clear line of sight for service. We just saw a slide on that, no? When you have satellite communication, you have dish antenna that are in contact with the satellite. So the one that corresponds to 3 will be satellite communication. Now 4, high-speed business class copper or fiber connection. What is that? It's SDSL. So DSL stands for Digital Subscriber Line. Oh, sorry. No. High-speed business copper, class copper or fiber optic connection is what? Is Metro Ethernet. So this one will be Metro Ethernet. Okay, let's see 5. Business class service that provide the same upload and download speed over telephone line. So over telephone line, we talk about DSL, which means digital subscriber line. And we have 2 flavors of DSL. We have symmetric DSL and we have asymmetric DSL. So at home, if you have AT&T, you have asymmetric DSL. What does it mean? You use the telephone line to get connected to the internet. But why it is asymmetric? Why in your house they want to put asymmetric DSL? Which means that in your house, the download bandwidth is higher than the upload bandwidth. Download is when I go from the internet to my house. Upload is when I go from my house to the internet. Why the download is bigger than the upload? Why for a house they do that? Yeah, so you don't provide services. You don't have a web server, you don't have a file server at home. So what you do is you surf the internet and you download things from the internet. So you use much more the download than the upload. It's why when they create internet over telephone line, for the people they did ADSL, because they will download more information than they will upload. There is much more traffic from the internet to your house than from your house to the internet. When you look at a web page, the server is in the internet, so you are fostering download traffic, which means from the internet to your house. When you download a file from the internet, you also send traffic from the internet to your house. So you seldom send traffic from your house to the internet, very little. It's why they use the asymmetric DSL. Now, a company will use symmetric DSL. Let's say that you connect a company through a telephone line. They will use symmetric DSL. Why? Because the company offers services. Look at JSU. JSU, here in this classroom, we download. But there is a bunch of people outside JSU that check the web page of JSU. That check, for example, Canvas. That check what else? What all of the services that we have? The registrar office. So we do provide service to the community. So we need something that is symmetrical, because there is a lot of traffic that go from the internet to us, because we access servers that are in the internet, but there is also a lot of people that are outside JSU that access the service that JSU provide. So in the case of a company, we need links that are symmetrical, because there is a balance between downloaded and uploading. So this SDSL is here, no? Business class service that provide the same upload and download speed over telephone line. So the one that left out is typically have low bandwidth. So something that have low bandwidth was the modem. The modem have very low bandwidth. Now, the standard that we use in cable TV is called DOCSIS. So if you have internet through Sparklight, which is one of the two internet providers that we have in Jacksonville, you use DOCSIS, and you don't know that you use DOCSIS, but you use DOCSIS. Now, if you have internet through AT&T, through the telephone line, you use ADSL, asymmetric digital subscriber line. Let's see question 4. What is a WAN? So answer A. A network infrastructure designed to provide data storage, retrieval, and replication. So answer A is a SAN, a storage area network. So this is a storage area network. Okay? This is not a WAN, a wide area network. B, a network infrastructure that provides access to other networks over a large geographical area. Yes, this is a WAN. Wide area network. I connect networks that are very far apart to each other in different cities of the same country or in different cities of different countries. Okay. A network infrastructure that spans a limited physical area, such as a city. That a MAN, metropolitan area network. A network infrastructure that provides access to a small area, to a small geographical area. How do we call that? A LAN, a local area network. So look, we have a lot of terms. We have a term that is band. Do you know what is a band? What is a band? A body area network. So today, you have on your body several devices that can communicate to each other. For example, you might have a headset. And this headset is wireless. It communicates with your cell phone. So you can listen to music from your cell phone using the headset. Or for the people that are sick, the doctor provides them some medical equipment that they put on their body. Those medical equipment have sensors and monitor the state of the patient. So those medical equipment normally send information to the cell phone, and the cell phone communicates that to the doctor. So when we talk about body area network, is the network that is over your body, and it's going to increase in the future. In this moment, it is not big. We have another term that is called personal area network. A personal area network is the network that I have in my office. It will span like maybe 10 meters on all the devices that are in my office that communicate to each other belong to the personal area network. Then we have the local area network. For example, here, with a limited span, we have a local area network. And all these computers are connected together through a switch. So local area network will cover the one floor of a building. It will cover one room, like here. After local area network, we have metropolitan area network. They cover a whole city. Then we have wide area network. City in the same country or city in different country. And we also have storage area network. So you see the number of terms that we have. Storage area network will be generally in a data center. And it will be all the network that we use to communicate the different storage devices that we have in the data center. Okay, let's stop for today here. In the next class, I will continue with lecture, and we will continue with exercise when we finish the lecture. Thank you, and I see you in 2 days.